Hi, my name is Madeline Hauer, and today I will be talking about the chapter Perceiving Color from our textbook. I chose this chapter because color is something we experience constantly. I think it is something many of us take for granted and don't appreciate enough. And after learning the science behind how we perceive color, my appreciation for sight and color perception has risen. We often think of color as something objects have, but color is actually something our visual system creates. Light hits an object, the object reflects certain wavelengths, and our brain interprets those wavelengths as color. For example, a red apple reflects more long wavelength light, but the apple isn't inherently red. Our perception makes it red. The visible spectrum ranges from about 400 to 700 nanometers. Shorter wavelengths are cooler colors like violet and blues. The medium wavelengths are green, and the longer wavelengths are warmer colors like yellow and red. Color perception has three main dimensions. Hue, which is what lets us know one color from another. Saturation, which is how pure or intense a color looks. And brightness, which is how dark or light it appears. These three dimensions help describe any color we see. An example of saturation is looking at a bright red stop sign compared to a faded red t-shirt. The stop sign is highly saturated, while the faded t-shirt is less saturated. One of the most important ideas in the chapter is trichromatic theory, or Young-Helmholtz theory. This theory says that we have three types of cone receptors in the retina. S cones for short wavelengths, M cones for medium wavelengths, and L cones for long wavelengths. Every color we perceive comes from different combinations of activity across these three cone types. Every pixel on your phone, computer, or TV is made of tiny red, green, and blue lights. Those three colors can combine to make millions of others, just like the cones in your eyes combine signals to create the full range of colors you experience. But the trichromatic theory alone can't explain everything, like why we see after images. That's where the opponent process theory comes in. This theory says that after cones respond, color signals get organized into opponent pairs: red versus green, blue versus yellow, and black versus white for brightness. You may notice when you stare at the red logo and then look at a white wall, you usually see a green after image. This explains why staring at something red for a while can make you see a green after image, and why we never see colors like reddish green or yellowish blue. The opponent channels work in a push-pull way, so only one color in each pair can be activated at a time. In this photo, I think is a very cool example of after-image illusion. If you stare at the three dots in the middle of the girl's face for about 20 seconds, the after image will appear. When I present a white background shortly, you will see the negative after image, which are the complementary colors of the previous photo you saw. Another important concept is the color constancy. This is our ability to perceive an object as the same color even when lighting changes. For example, a white shirt still looks white whether you're indoors under yellowish light or outside in a bright light. Our visual system does this through things like chromatic adaptation, where it adjusts to the overall lighting, and through context, surrounding colors help the brain figure out which the actual color should be. This is part of why illusions like the dress went viral. Our brains were making different assumptions about the lighting. Finally, the chapter covers different color deficiencies. Some people are dichromats, meaning they're missing one type of cone. Depending on which cone type is missing, they have trouble distinguishing reds, greens, or blues. Others have anomalous trichromancy, sorry for the mispronunciation, where they have all three cones, but the sensitivity of one is shifted, so colors don't look quite the same. And in rare cases, people can experience color vision loss from brain damage. This is called cortical achromatophasia, and I probably pronounced that wrong too. To wrap this up, color perception is the result of complex interactions between light, receptors in the eyes, and neutral processing in the brain. The combination of trichromatic and opponent processing theories helps explain how we experience the rich, detailed world of color around us. Thank you for listening.